in this course, what we're trying to do is we're trying to develop a science of uncertainty. How do we deal with outcomes that can be random, right? So we find uncertainty everywhere, right? If I drive, I might get into a traffic accident, right? Probably I won't get into a traffic accident. People don't get into traffic accidents every day, but I might. And I assess that the probability is enough that I want to wear a seatbelt. Okay? The campus could be destroyed by a meteorite, but I really don't worry about it. Somehow I assess that that is very unlikely compared to the likelihood of getting into an accident. Okay? So we have an intuitive idea of something being likely, unlikely, certain, impossible. Right? So we want to now make that, concrete and numerical. We want a mathematical way of talking about such things. Okay? So, if you pay attention through this course, then at the end of it, you will have enough math. We will have developed enough of this science of uncertainty that you could, for example, make a budget for things, let's say widows' pensions. It's uncertain how many widows there will be, but we'll have some idea of how to budget resources. We will be able to interpret medical tests, right? Repeated studies have shown that doctors misinterpret medical tests all the time. The majority of doctors misinterpret the results of medical tests. When you get a test and it says you have COVID, they misinterpret the probability that you actually do have the disease. Okay. Now, in any course of mathematics, there's usually some underlying idea of sets, and there are particular sets that you deal with. In this course, the set that we deal with is called the sample space. So we're always referring to the sample space, and we are always referring to subsets of the sample space. So you probably know everything about, well, everything I'm going to tell you here about sets. I'm just going to review it to make sure that you know, if there's something you've forgotten, you can note it down. The things that we're going to use in this course, I need to make sure that you know that. Okay? So, let's go. Okay? What's a set? Informally, a set is a well-defined collection of objects or elements. Okay? The members of a set are called elements of the set. Okay? So, if A is the set of all students registered in this course, each student is an element of, every student here is an element of A, and I am not an element of A. Okay? I'm going to write this notation. That means A is an element of A. This notation means B is not an element of A. Okay? There's a set that we also have to refer to. We use this will come up. When there's zero probability of something happening, the empty set, that's a set which has no elements in it, so we call it the empty set or the null set. And the notation we use for that is either curly brackets with nothing inside of them, or this Norwegian letter which looks like an O with a slash through it. Okay. Subsets. So we're going to be talking about subsets of the sample space all the time in this course. Okay. A is a subset of B if every element of A is inside of B, is also an element of B, and this is the notation for subset. Okay, so for example, every element of A is in A, so A is a subset of A. Okay? And we take it as an axiom of our set theory that the null set is a subset of every single set. Right? Every set has a bunch of subsets, and one of those subsets is always the null set. Okay? We will say that A is equal to B. What does it mean for set A to be equal to set B? It means that A is a subset of B, and B is a subset of A. Every element of A is in B, and every element of B is in A. Okay, complement of a set. So the complement of A in S means that I've got some set S. There's a bunch of elements in S which are in A. A is a subset of S, right? And then there's all these elements which are in S, but they're not in A. So if I took S and I ripped all the elements of A out of it, what's left over is the complement of A in S. Okay, so for example, if I let the integers be the set S, right? And I let A be all the negative integers, what's the complement of A in the integers? Right, the positive integers plus 0 is the complement of A in the integers, in the set of integers. Okay? Okay, so I'm going to use, when I write complement, I'm going to write the complement of A as A with a prime symbol on it. Okay? Some textbooks use A with a superscript C. So, depending upon which textbook you use, you'll either see this or this. I will try to use this with the prime symbol consistently, right? If I accidentally write C, you'll know that I mean the same thing. Okay. And once again, the complement of A in S are those elements B which are in S, and at the same time, they are not elements of A. Okay. Intersection. Suppose A and B are sets. This is read as A intersection B, or the intersection of A and B. That means elements which are in A and elements which are in B, both at the same time. Okay? So, you might look at it like this. Here's A, here's B, and there are some things which are in both, and I'm calling that the intersection of A and B. Okay? What's the intersection of the positive integers and the negative integers? All of the integers except 0. Okay? Okay, so, oh, sorry. Intersection, not the union. Right, so, once again, the intersection of the positive integers and the negative integers? Right, the null set, there's nothing common between those two sets. So the intersection is the null set. Okay? Okay, union. A union B, so I have a set A, I have a set B. A union B consists of the elements of A, something which is in A, or in B, or it could be in both. So I have A and I have B, and everything that's here or in A or in B or in the intersection, put all of those elements together and you get a set which we call A union B. Okay, here. The union of the positive integers and the negative integers is all the integers except 0. Okay, we're going to be talking about intersections and unions, so we need to know a few rules about them. All right, we'll be using these rules through the course. I just want to probably already know them, but just to make sure. Okay, A union B is the same as B union A from the definition. A union B union C, it doesn't matter which, you just take which order you take the unions in. If you're taking intersections, again, it doesn't matter whether you take the intersection from the left or the intersection from the right, you'll end up with the same thing. Okay, so those are called associative laws. Distributive laws, okay. Supposing you have a union and you intersect it with a set, right? So A union B intersection C is the same as A intersection C, B intersection C, and then you take their union. So you have this distribution law. Okay? And if you have A intersection B and you union with C, you can take A union C and intersect it with B union C. And, you know, in this course, you just, whichever one is more convenient to you. Sometimes it's more convenient to write it one way or to write it the other way for a particular calculation. So rewrite these things in the form which is convenient for your calculations. Okay, we were talking about complements. So what if we take the complement of a union? So De Morgan's laws say that if I take the complement of A union B, that's the same as taking the intersection of A complement with B complement. Okay? And the other De Morgan's law is that if I take the complement of A intersection B, that's the same as doing A complement union with B complement. And again, there will be times in this course when it's easier to do the calculation with one form or the other. They both mean the same thing, but you rewrite them in the form which is convenient for your calculation. Okay. So now it turns out that the set that we want to talk about and the subsets and its subsets, those are called the sample space and events. Okay? So we have an experiment which generates a set of data, typically random data, right? So I can record a stock price every day, the closing stock price every day. I don't know what it's going to be. It's some set of random data, for example. Right? Now, or just about anything. There are lots of things where the outcome are not certain. So you imagine all of our experiments are going to be thought experiments. Okay, so if I pick up something and try and hit you with it, I might decide I'm going to record a hit or a miss. So my sample space is the set of all possible outcomes. We usually write S for the sample space. So the two outcomes that are possible for S are hit and miss. Okay? And this terminology here, putting it S between vertical lines means how many elements are there in S? In this case, there are two elements of S. And here we say, we read this as cardinality of S is equal to 2. The number of elements in S is 2. Okay. Roll a fair die and record the outcome. So what does the outcome look like? What are all the possible outcomes? Rolling a 1, 2, 3, 4, 5, 6. Okay, so we have a set of all possible outcomes S. These are the possible rolls of the die. Okay, and what's the cardinality of this S? 6. Good. Cardinality of S is equal to 6. Okay, another experiment. We're going to record the time till failure of an electronic device. So we turn on a device, and starting from time equals 0 to time equals whatever when it fails, so we record that. So what would the sample space be for this? Yeah, the sample space would be 0 to, in principle, the device could keep working forever, right? So this time we'll write S in this interval notation that we remember from calculus 1, right? 0 to infinity. And we might write that the cardinality of S is equal to infinity. Yes?
Say infinity inclusive union.
Why have I written infinity?
Because say infinity inclusive union, 0 to inclusive.
Oh, right. Why do we have a round bracket instead of a square bracket, meaning that there's inclusion? Because you never get to infinity, and infinity isn't a member of the real number system, actually. Okay. As I said, the set of all possible outcomes of the experiment is called the sample space. Okay. Subsets of the sample space are called events. So all the time in this course, we will be dealing with the sample space, and we will be dealing with the subsets of the sample space, which are called events. Okay, so for the rolling the die example, this was the sample space, right? And here are some subsets of the sample space. So subsets of the sample space are events. So I have an event A, and I have an event B. The event A is rolling a 1 or a 2. The event B is rolling a 2 or a 3. Okay. Okay. So the electronic device example, getting back to that, the sample space was this interval from 0 to infinity. And here's a subspace. The device ran for somewhere between 1 and 10 time units. Right? This is a subset of the sample space. So A is an event. Yeah.
सर क्योंकि A का सेट जो है वो एक इंटरवल है, तो हमने वो इंटरवल को हमने कर्ली ब्रेसेस में क्यों निकाला?
Oh, you could write curly bracket x runs 1 less than or equal to x less than or equal to 10 if you wanted to. Write it in the curly bracket notation. But I mean, this looks a little more convenient. Right? Okay. Okay, so if you had an event A, its complement is also a subset of the sample space. Right? So a complement of A is also an event. So remember we had the rolling the dice example. We had events A and B. And now, what's the complement of A and S? Yeah. Rolling a 3, a 4, a 5, or a 6. What's the complement of B? 1, 4, 5, 6, right? So, to find the complement of A, everything in S and throw out rolling a 1 and rolling a 2. Find the complement of B, everything in S, but throw out 2 and 3, everything in B. Okay? So, as you said, these are our A complement and our B complement. Right? So these are new events also, subsets of S. subsets of the sample space. Okay, we had A was the interval from 1 to 10. That was an event inside this S. This is A. 0 to 1, union 10 to infinity, but not including 10, not including 1. Okay, so this is what the complement looks like. Intersections, well, we already discussed intersections. In our particular case, in the rolling the die example, this was our A, and this was our B. So a new event, event A, event B, a new event, A union B is what? Rolling a 1, a 2, or a 3. What's the intersection? Rolling a 2. What if we had, in the electronic device example, A is the interval from 1 to 10, B is the interval from 11 till 30. What's the intersection? Null set. So we're going to use a particular terminology here, right, through the rest of the course. If you have events A, subsets of S, event B is a subset of S, and it turns out that the intersection is empty, they have no common element, then the terminology we use is that the events are mutually exclusive or disjoint. So disjoint events or mutually exclusive events means that their intersection is empty. We've already talked about unions. So if I have A union B, for the dice example, what's the union? 1, 2, 3.
Is the mutually exclusive property look on the other way around? Like, I can null set or the mutually exclusive. It can open be a statement next sentence.
Well, it's a definition. So it's an if and only if. Yeah. So saying that two events are mutually exclusive is the same as saying that their intersection is empty. Saying that their intersection is empty is the same as saying that the events are mutually exclusive.
Sir?
Yeah.
Does mutually exclusive also mean that they do not occur in the physical sense? Like, let's say we have an event A in which we roll dice 2, 3, and event B in which we roll dice 2, 4. So these events are not mutually.
Yeah. The new, okay, so if you have, when we assign probabilities, we're going to assign a probability of 0 to the empty set. So the intersection is 0, it means that these two events don't occur at the same time. Okay, 1 through 10, 5 through 30. This is one event. This is another event. What's the union of the two events? 1 through 30. Very good. There's a list of exercises depending upon which textbook you want to look at. The required textbook is Walpole, but you also might want to look at Ross. He also has some nice exercises. So you might want to do these from Ross or these exercises from Walpole. Okay? All right, so are there any questions about, yeah? No, we don't. Okay. It turns out that for certain situations, being able to count the number of elements, getting the cardinality of S, or being able to find the cardinality of the subsets of S, the events. So in certain situations, that will help us work out the probability that we're going to associate with events. Okay? So we need to know a few rules for counting. Okay? Let's start with an example. I'm going to toss a coin twice. I'm going to record head or tails with the tosses. Okay? In order. So I could get a head or a tail. After getting a head, I could then get a head, tail, or if I got a tail first, then tail, head, tail, tail. So there are 4 possible outcomes. If I'm recording in order, whether I get a head or a tail on the first toss and on the second toss, then those are the elements of my sample space. And there are 4 such elements of the sample space. Okay? Okay, and if we go back here, well, we had two elements for the first. We had two possible outcomes for the first. Huh? Then we had two possible outcomes for the second toss. And it turns out that we ended up with 4 outcomes, right? Okay? So what if we roll a 6-sided die? And we do it twice. So we sort of, yeah, it seems obvious we would have 36 possible outcomes. Right? Okay? So now we're just going to, whatever you did in your head to get that result, 2 times 2 and 6 times 6, right? Well, there's a name for that. It's called the multiplication rule. Okay? So the multiplication rule is going to help us work out the cardinality of sample spaces and their subsets, which in turn will help us work out probabilities a little later, okay? So, multiplication rule. So multiplication rule says this. Supposing that something is to be done in 2 steps, and there's n1 ways of doing the first step, and there's n2 ways for each one of those n1 ways, the next step can be done in n2 ways. Then the number of ways of doing the complete operation is n1 times n2. So that's what you were doing when you said, okay, 2 times 2 and 6 times 6 in the previous example. You were basically applying this multiplication rule, n1 times n2. Okay, n1 times n2 is the multiplication rule. Now, what if the general rule? What if there were k steps to doing an operation? The first step can be done in n1 ways. For after each one of those n1 ways, there's n2 ways of doing the next step. There's n3 ways of doing the next step, up to nk ways. So the multiplication rule says, the general multiplication rule says, that the total number of ways of performing the operation is n1 times n2 times n3 and so on up to nk. All right? So, I have 5 different shirts. I have 7 different pants. How many shirt-pant combinations do I have? Right. 5 ways to pick the shirts. Once I've done that, that's the first step of the operation. 7 ways then to pick the pants. 5 times 7 is 35. I apply the multiplication rule. There are 35 ways. Yeah.
Would this also equal to the cardinality of the sub?
Yeah. So now if we said, what are the possible outcomes? Well, let's say that the sample space is the set of all possible outcomes of selecting a shirt and selecting a pant. So the cardinality of that sample space, if I record the shirt and the pant that I selected, the cardinality of that sample space is 35. Okay. I'm going to construct a 2-digit number. Each of the digits has to be 1 through 9. Each digit can only be used once. So 2 is not allowed, for example. Okay? So, how many ways? 72. Right. There are 9 ways of selecting the first number. Now you've used up one of the numbers, so there's only 8 ways of selecting the next number. 9 times 8 is 72. Okay? Any questions about that one? Okay. Be sure to ask your questions as they come up. Okay? I have to construct a 2-digit number, and the first number has to be 2. How many ways are there? Okay? Right? The first one has to be a 2, so there's only one way of doing the first step. I've used up the 2, so there are 8 numbers left to use to pick the second number. So 1 times 8, according to the multiplication rule.
The question we dealt with right now,
Yeah.
it was framed as we have digits from 1 to 9. What are the possible combination of two-digit numbers from this missing? So would that be the same?
Okay, if I didn't have any condition, if I said 2-digit numbers and you're allowed to repeat, then you can pick 9 for the first one, and you pick 9 for the second one. So 9 times 9. Okay? All right. So one thing that we're going to need to do, we have ideas of permutations or rearrangements. And we want to be able to count how many different permutations there are in some situation. Okay? So a permutation is the arrangement, is a rearrangement or an arrangement of all of a set of objects or a certain set of objects, a subset of those objects. Okay? So I don't know. So if I had a bunch of numbers, I had 5 numbers, right? And then I started interchanging the numbers. If I interchange the first and the last, right, and I switch, then that would be a permutation of that string of numbers or letters or symbols. Okay? So I have the letters A, B. So there's a string of 2 letters, the 2-letter string A, B. So that's one permutation or one arrangement. Now, if I still want a string of 2 letters, one after the other, what can I do? I can write BA instead of AB. All right, so there are 2 arrangements. Are there any other arrangements? Right? So we say that there are 2 arrangements of this 2-letter string. Okay? Or we say there are 2 permutations of 2 distinct letters or 2 distinct symbols. Didn't matter that they were A and B. It could have been 1 and 2. It could have been box and triangle. Right? Just a string of symbols. Right? Okay. So I want to write 3-letter strings using the letters A, B, and C with no repetition. Okay? How many? Now let's use the multiplication rule to do this. What would you get?
6.
Okay? So there's 3 ways of picking the first symbol. Now you've used up one of the symbols. Then there's 2 ways of picking the next symbol. And then you have only 1 symbol left, so you have to pick that one. So there's only one way of getting that one. So the multiplication rule says 3 times 2 times 1 way of writing 3 distinct symbols in a row. How many ways of writing 4 distinct symbols in a row? No repetitions. Right? 4 ways to select the first one. You've used one of them. So 3 ways to select the next one, 2 ways to select the next one, 1 way to select the next one. So 4 times 3 times 2 times 1 according to the multiplication rule. Okay. All right, so that could get tedious, right? If I said there are 57 distinct symbols, how many ways to write them all in a row? Instead of writing 57 times 56 times, we write 51 factorial. Okay, the exclamation mark there is read as factorial. So n factorial is n times n minus 1 times n minus 2, all the way down to 1. Okay, so there are n factorial ways, according to the multiplication rule. There are n factorial ways to write n distinct symbols in a row without repetition. Okay, and it's convenient to define 0 factorial to be 1. And also note that n factorial is the same as n times n minus 1 factorial. Sometimes that will help you to rewrite things when you're doing some calculations. Okay, so 4 distinct symbols in a row without repetition. How many ways? 4 factorial. We have 4 distinct symbols. Well, let's call them A, B, C, D. We need to select one of those 4 distinct symbols. How many ways are there? There are 4 ways. All right? Or another way of doing it is to imagine that you're going to break it up in these 4 symbols, you're going to break up into 2 piles. One pile will be selected, and one pile will be unselected. Okay? So then if you want to rewrite that 4 using this factorial notation, right? I could start by saying I'm going to select the 1. There's 4 ways of doing that. Or I'm going to say that there are 4 factorial ways, but let's say I selected the C. And then there was, let's say, BAD here. Okay? So there are 4 factorial ways of writing this. But I know that that's not the right answer, right? How can I fix the answer of 4 factorial? Well, when I say 4 factorial, I'm including all the arrangements of the letters that I did not select. Okay? And there are 3 factorial ways in those letters. But if I selected this one, none of the 3 factorial rearrangements of these matter. Right? The arrangements of the unselected letters don't matter. Okay? So when I wrote 4 factorial, I overcounted by 3 factorial. So I have to fix that. I overcounted by a factor of 3 factorial, so I divide out 3 factorial. Okay? Now that's a very complicated way of saying 4, right? 4 factorial divided by the ones that I didn't select were 4 minus 1 factorial. Okay? But that way of thinking will be useful as we go along. Okay? Okay? 4 letters, A, B, C, D. This time we're going to choose 2 of them. The order matters. And then the rest are discarded. They're left over. The order we write them in doesn't matter. Okay? So if I write how many ways are there of selecting when order matters? How many ways are there of selecting four symbols from two distinct symbols from four distinct symbols without repetition? Okay? One way to do it would be, say, multiplication rule, 4 times 3. Okay? But if I want to write that for some reason in the factorial notation, how would I write it? Right? Right? It would be 4 factorial over 4 minus 2 factorial. If I write 4 factorial, I am overcounting by a factor of the rearrangements of things that are not selected. They don't matter. So I divide out by that overcounting. I divide out by 4 minus 2 factorial. Okay. I have n distinct symbols. I'm going to select r of them without repetition. So I've got n in a box. I'm going to put r of them out on the table in a line. And then there will be n minus r left over. So how many ways are there of doing that? Right? N factorial. Imagine laying out all n in a row. There are n factorial ways of doing that. But in n minus r, it doesn't matter because those haven't been chosen. I'm not going to look at them. So I've overcounted by a factor of n minus r factorial, and I'm going to divide that n factorial by n minus r factorial to correct for this overcounting. Okay? So the number of ways to take r distinct objects from n distinct objects is, without any repetitions, is n factorial over n minus r factorial. Okay? People also use this notation, n pick r, for this. Okay, I usually don't do it, but you might see it in your textbook, so I've put it in there. Okay? But anyways, this n pick r means n factorial over n minus r factorial. Okay? Okay, so 30 distinct symbols, 2 are to be picked in order. How many permutations? Right, 30 factorial over 28 factorial. Okay, which is the same as 30 times 29, which you could have gotten from your counting rule. Let's skip the discussion of circular arrangements. Okay. Okay, we've been talking about distinct objects. That's it, right? That sometimes there are objects which are not distinct, right? Or objects which are equivalent, right? So what kind of permutations can we get there? Okay? So for example, we have a letter string, W-O-R-D. Well, okay, so we have a word, A-A, just a string of 2 letters. And the letters are not different. If it was AB, how many permutations would we have? We would have 2. But how many permutations of AA are there?
1.
That's 1. Okay? So when things are not distinct, then the answers are a little bit different than what we've discussed, right? So we're going to talk about that for a bit. Okay? So let's say let's say I have 3 letters, AAB. And I'm going to make a 3-letter string. Okay? Each one will be used only once. Note that 2 of the letters are identical. How many ways? 3, 2. Okay, so there's 3 ways. Basically, you can choose where to put your B. And that sets where the A's are. And there are 3. You can put B in the beginning, the middle, or the end. So there are 3 ways. Okay? Now, using factorial notation, how would we do it? We would say there are 3 factorial ways of arranging 3 distinct symbols in a row. But 2 of them are the same. So if I interchange those, the letter string doesn't change. So I've been imagining that 2, when I said this, that was as if those 2 were distinct, but they're not. And those 2 would contribute 2 factorial, a factor of 2 factorial. So we have to correct this. So we have to divide by 2 factorial to make our correction. Okay? So then we have 3 factorial divided by 2 factorial. Okay, so now, yeah.
So we're not choosing the actual positions, right? So why isn't it 3 factorial over 3 minus 2 factorial?
Let's see. So we can have AAB, we can have ABA, or we can have BAA. So we can have 3. So if I write 3 factorial, then I've got to divide out 2 factorial to make it come out to 3. Okay? The 2 factorial is saying that when you wrote 3 factorial by itself, you were treating these 2 A's as if they were distinct. And they're contributing permutations of those A's, if they were distinct, would be 2 factorial ways. So you've overcounted by a factor of 2 factorial. So now we're going to divide it out to get the correct answer. Okay? Now, what if I had n distinct symbols? And 1 of them are the same, and 2 of them are the same, and 3 of them are the same, and so on. Well, if I pretend for the moment that they're all distinct, then the answer would be n factorial permutations. But n1 of them were the same. And interchanges of those n1 symbols don't change anything. So they were contributing a factor of n1 factorial in my n factorial, but they shouldn't have been. So I'm going to divide out by n1 factorial. And so on. If I had n2 objects which were the same, they were contributing n2 factorial to my n factorial answer, but they should not have been, because interchanges within those exactly the same symbols don't produce a new permutation. So I'd have to divide out that n2 factorial, and so on. Okay? Yeah.
Can we also write it as n factorial over n minus k factorial?
In some cases, but not always. Okay? Okay, all right. So 3 white cards, 3 black cards. They just show white and black, okay? They're laid out in a line. How many distinct permutations are there? Okay? Right? If they were distinct, I would say 6 factorial. But the 3 white cards were the same. So interchanges within those 3 white cards are contributing 3 factorial to here, but they shouldn't be, because interchanging them doesn't change anything. So I have to divide out by that 3 factorial. There were 3 identical black cards. Interchanges within those ones, just within the black cards, are contributing 3 factorial to the 6 factorial, but they shouldn't be. So I divide that out. I take those away. Okay? So 3 white plus 3 black factorial over overcounting of the whites, factor of 3 factorial, and overcounting of the blacks, divide out 3 factorial. Okay, so that's the answer. Partitions. Try another problem. I have 12 shirts. They have to go in an upper drawer and a lower drawer. Okay? I'm going to put 6 in the top and 6 in the bottom. I don't worry about order in the drawer. I just worry about whether it's in the top, the shirt is in the top drawer or the bottom drawer. But within a drawer, I don't care about the order. So how many arrangements are there? I have 12 shirts, right? So I can write shirt A, shirt C, shirt D, and so on. There are 12 ways of arranging those distinct symbols. But I said that order within the first drawer doesn't matter. So if I interchange 6 symbols, I do the permutations of 6 distinct symbols here, they would be contributing 6 factorial. But they shouldn't be, because I'm saying order within a drawer doesn't matter. And here there's 6 of them, and they're contributing 6 factorial to the 12 factorial, but they shouldn't be because I said order within a drawer doesn't matter. Okay? So 12 factorial divided by overcounting of 6 factorial here and overcounting of 6 factorial there. Okay? Okay. Now I'm going to put 7 shirts in the top drawer, and I'm going to put 5 shirts in the bottom drawer. Order within a drawer doesn't matter. Or if you imagine 12 distinct objects, I'm going to put 7 in one box, and I'll put 5 in the other box, and I don't care how they're messed up in the box, in each individual box. Okay? How many ways? Right. So how many ways, okay, so we can look at it as how many ways of dividing up 12 distinct objects into 2 boxes, such that 7 go into one box and 5 go into the other box. Okay, so imagine we're rolling them out in a line, and then we make the decision, okay, here, these 7 over here, they go into one box. These 5 over here, they go into the other box. So when I put them together in a line, wrote them out, put them in a row, there were 12 factorial ways of doing that. So, oh yeah, I remember that rule, n factorial. So 12 factorial. Then you say, but once they're in this box, their orders don't matter. So if I rearrange them in this box, I don't think of that as a different permutation. Okay, so then those are contributing 7 factorial to the 12 factorial, which they shouldn't be. So dividing by 7 factorial. And then in the other box, there are 5 of these objects, and I rearrange them, but their rearrangements don't matter. And they're contributing 5 factorial to this 12 factorial, but they shouldn't be. So I divide out that 5 factorial. Okay, so this illustrates the idea of a partition. You're partitioning n objects into R cells, R boxes, and then within the box you don't care how they're ordered. Okay? So the general rule for that is n factorial divided by the number in the first box factorial, second box factorial, number in the third box factorial, and so on. Okay. 52 cards in the deck. 52 distinct symbols. They have to be divided about, 4 players, 13 cards each. How many ways? Yeah?
52 factorial into 13 factorial into 13 factorial.
Yeah, right. 52 factorial, if I laid them out. Now I take 13 of these and I give them to a player. Now, he puts them in the hand, but I don't think that hands matter how you arrange them in your hand, right? It's still the same hand of 13 cards. So that's 52 factorial divided by an overcounting of 13 factorial, because it didn't matter what happened, how that player arranges them, right? And the same for the second, third, and fourth. So 52 factorial over 13 factorial to the fourth power.
Sir?
Yeah.
Is saying that how many ways are there to divide a deck of 52 cards into hands of 13?
Yes.
The same as saying how many permutations are there of 52 cards.
No, permutations of 52 cards sounds like 52 factorial to me, right? So this is different than that.
But in the previous example,
Yes.
we had to divide cloths into 7 and 5.
Right. So we divided up things into boxes, and within the boxes, within the cells, the ordering doesn't matter. Okay? So this is saying I'm dividing them up into boxes with 13 each, and within each one, the ordering, within each box or each cell, the ordering does not matter. Okay, so a special case, we say combinations, and these are partitions into 2 sets, right? Instead of R cells in general, we're going to partition into 2 sets. So now, what would that be? It's n objects, distinct ones, so n factorial, and then they're divided up into 2 piles. In one pile, you've got R objects, and so in the second one, you have n minus R objects. And we don't care about those R objects in the first box, how they're arranged within the box. So we divide out by R factorial. And the next one, we don't care about those arrangements of those n minus R within the box. So there's n minus R factorial. Okay? So that's the number of ways of saying n objects, put R in a box, and put n minus R in the other box, and within the boxes, we don't care about the ordering. Okay? In the special case of choosing 0, right? How many ways are there to put n objects into 2 boxes where all n go into one box and the other box is empty? Yeah. Yeah.
So you're talking about 2 boxes. For example, there are 3 boxes.
Oh, well, then that's the previous case of combinations. This is a special case of a combination, partitioned just into 2 cells. Yes, the general formula we already discussed. That was, right? That was the general formula for partitioning. into R boxes. And in this case, we're specially saying for combinations, we're saying partition into 2 cells. Yes?
In the notation, why in the combination, why did we write R, comma, and minus?
Oh, all right. Why did the notation change? Okay, the reason the notation changes is that if you have R, then it's understood that, right? So you're right. Using the previous notation, we could have written R, comma, n minus R. But since the n minus R, once you say R, n minus R is understood. So we don't bother to write it in that case. Okay? Okay, so as I said, for 0, there's one way of putting n into a box and putting none into the other box. There's one way of putting n into a box and none into the other box. Once again, if you look at the lecture slides, there's some suggested exercises. You should also do, on the LMS, there's also some exercises you might want to try to see if you understand them. Okay, I'll see you on Thursday.